Welcome to Chemistry 111. We'll be continuing where we left off. We had previously discussed how to utilize our Lewis structure to determine the electronic formula or the electron domain, the electron geometry or the electron domain geometry, and then take that to the molecular geometry. We finished up by just looking at the shapes of large molecules. So, in mind that one of the more important things we use this for is determining molecular dipoles. At the end of the previous chapter, we discussed essentially bond dipoles. We looked at here's the electronegativity of this atom, here's the electronegativity of this atom. If they are significantly different, there is a partial charge separation. It's not a full ion, but a partial separation, which leads to what we called a delta positive and a delta negative. And these separation of charges creates two poles on a bond, thus the dipole. Now, within a molecule, we can have a series of dipoles, where each dipole with each bond. And we're going to look at each one. And the important thing to note is that all these guys are going to add up and subtract depending on some simple physics and math. They're essentially a little bit of vectors. In physics, you might learn that if I have a vector pulling to the right by a strength of 2, and I have a vector pulling to the left with a strength of 2, the net pull would be 0. Even though you have two things pulling in opposite directions, they cancel each other out. An object would not move. And if I had one guy pulling with a strength of 2 to the right, and one guy pulling to the strength of right with 1, they would add up to a pull of 3 to the right. So we can add vectors up and subtract vectors depending on equal and opposite. If a guy is pulling in a diagonal direction, that diagonal vector is actually a sum of the up and the right. For example, if I'm pulling up and to the right, upright diagonal, that's a sum of two vectors made up of the up portion and the right portion. Now, essentially here, what we can look at is the strength of the dipole would be the magnitude of the vector. And where this bond is located will have to do with the XYZ coordinate plane and our molecular shape. And the important thing here is that in order for a molecule to be polar, to have a dipole within the molecule, there has to be a region of electronegativity difference within that molecule. There has to be one part of the molecule that is positive, one part of the molecule that is negative. If you cannot determine which side or which face is positive and which face is negative, it is considered nonpolar, and that's going to control the reactivity. So I'm going to quickly draw something. This is at the beginning of this chapter. We asked, why is CO2 different from water? CO2 different from water. By itself, a CO double bond is polar. C is two atoms to the left of oxygen, meaning the oxygen is pulling electrons from the carbon. But because this is linear, this oxygen is pulling electrons from the carbon in the other way. Because it's linear, they are pulling net opposite. And so the net dipole is 0. They cancel each other out. The water being bent has a different situation. This hydrogen, is pulling up and to the left. This hydrogen is pulling up and to the right. The left portion and the right portion cancel each other out. But both atoms contain a up portion. So the net dipole would be straight up. And so would say this is the top part of this oxygen is negative. The bottom part of this molecule is positive. So essentially, the hydrogen portion is positive, the oxygen portion is negative. And we can do this with all molecules. You have to think of a little bit of geometry, and you kind of have to hold some models in your hand in order to kind of do this. But what you can see is if I have something like CF4, each and every CF bond are polar. This is one of the most polar bonds we could possibly have. We could have something slightly more polar, but because of the rearrangement of this tetrahedron, you may not see it right now, but this fluorine is equivalent to this fluorine, which is equivalent to this fluorine, which is equivalent to this fluorine. This guy is a geometric, the equilateral pyramid. So I could rotate this guy to here. So even though this guy's pulling up and there's three guys pulling down, they're pulling down at such an angle that they add up to cancel out the up. I have one guy pulling left, but these guys are pulling right, and two guys pulling right, but they're pulling right at a lesser angle. And so these two lesser angles add up to the one guy pulling left. You have one guy pulling front, one guy pulling back. They cancel each other out. Even though this is an incredibly polar bonds, they all cancel out. So this is no dipole in this molecule. However, I take even just one atom off and change it for a hydrogen. Suddenly we can look, this bond is not polar. So even though the left and the right still cancel, the front and the back still cancel, all atoms are pulling down. So the net dipole here would be straight down through the bottom of this molecule. And so you will, in lab, we will play around with models. Hopefully you can hold this in your hand, rotate it around, and see that this guy would be pulling straight down through the bottom of this pyramid. And so that would be a dipolar molecule. It's a little bit easier to see in, say, a trigonal planar, like BF3. BF3. That these F's are the hypotenuse of here. A hypotenuse is, remember, a squared plus b squared equals c squared. We have their c squared. That's our c. This guy's just a straight line. So we have b squared plus the b squared adds up to that guy. It's up to that guy. So this guy these two guys add up to cancel that guy. This left fluorine cancels the right fluorine. And so this guy is molecularly neutral. If I do, instead of BF3, I say BFFCl. Cl is different from fluorine. And so because it's different, they don't all cancel out. It's a tug of war, but one side has the anchor. One side has the person who, I don't know, broke his arm. So he's not going to be very good at pulling. And so chlorine is actually weaker than fluorine, so it's going to be pulling away from the chlorine. And so we're going to be able to do that. Consider these things as we make the molecule, and that will be part of the lab that some of you will be doing today. We'll be making some molecules, drawing the Lewis structure. We will be determining the electronic geometry, determining the molecular geometry, and finally determining the dipole. Well, there may be one other step, but that's the majority of what we'll be doing in lab. We'll be picturing this. If you don't need to make the models, you don't have to make the models, but the models are there to help you see these guys a little bit better. See these shapes. You can hold them in your hand. You can rotate it around and go, oh, that's what that stupid thing's supposed to look like. You can actually see it. Okay. So here's some, oh, if it's gonna, come on. Okay, how far is it gonna jump forward? Okay, thank God. So here's some more examples. Polar versus nonpolar. So in this case, the arrow part of this is actually the positive side. This structure, HCl. The chloride is more negative than the hydrogen. That's pretty obvious because it's linear and they're two different atoms. Water. We already did water. This guy is dichloromethane. So it's CH2Cl2, dichloro. So you notice that here, these hydrogens are almost nothing. The chlorines beat the hydrogens. We have a guy pulling up and to the right, a guy pulling up and to the left, and because we both pull right, the net charge is just straight right between the two. Split the difference. All the bottom structures, while having polar bonds, are considered nonpolar. This guy is what, like carbonate? Carbonate, drawing this guy, you see, well, there's this oxygen is pulling down, this guy is pulling down. They canceled up, but the up. Because if I rotate this, if you say, oh, the up guy wins, the up guy wins. If I rotate this guy goes to the up position. So this guy, the top guy can't win if I can put the right guy into the top guy's position. If I can rotate this molecule and replace one winner with another winner, they can't all be winners. There's no participation trophies in polarity. So CO2, we just did this one. This is one kind of a little weird, but this is, if I'm not mistaken, SF6. This is an octahedral structure. Even though all these bonds are polar, octahedral all cancels out. And this one, you can see it very perfectly. Up is canceled by down. Left front is canceled by right back. Right front is canceled by left back. Each atom has an equal and opposite atom pulling against it. So there's no way there could be any degree of polarity because each atom is equal and opposite. So they cancel out. Just a giant tug of war between the nuclei of the satellite atoms. Now, that is but one portion of this chapter. There is some more of this chapter that's a little bit trickier. We'll try to go through it. We'll try to explain it. But this is getting into the weeds of what is actually going on. The Vesper model does a good job of picturing what the atoms look like. But the question becomes, how do they make these bonds? How do they make these 4 bonds, these 3 bonds, these 2 bonds? Because if you remember in chapter 6, we introduced, actually say chapter 4, we introduced the s orbital, the p orbital, and the d orbitals. The s and the p and the d, those 3, and the f, of course. And those have certain types of overlaps you can imagine. Down there, it's a pretty straightforward one. An s and a p, those can very easily overlap to make a single bond for the HCl, and that will work. But in other structures, it's not going to work quite so nice, and so we actually need a theory. So we're going to introduce the valence bond theory to understand how bonds actually form. So the first thing to note is that the 2 electrons that orbit of the orbitals will begin to overlap until they reach an optimal potential energy minimum, where the electron spin become paired as they occupy this overlapping region. So essentially the hydrogen atom is going to get close enough to the chlorine atom so we have an optimal overlap. Optimal overlap. You get to over here, we have distance. As it gets far away, there's less attraction. There's almost no attraction here. It's 0 attraction. Getting closer and closer, the electrons are attracted, the minimum. And then when we get too close, the energy suddenly drops off and actually goes positive, which means it is not good. Essentially, we go from attraction to repulsion. We get the nuclei of the 2 atoms are getting too close together, so the positive charge of one nuclei starts repelling the positive charge of the other nuclei, and so they start shooting away. So there's a maximum bond distance that has the best energy of the attraction. And that's pretty easy to understand for H2 or HCl. H2 would just be 2 s orbitals overlapping. There's H, there's another H. There's a maximum, there's a ideal overlap position. Yeah, a little bit of reflection on there. Not sure I can really help that. But for any other atom, it becomes a little bit harder. If you imagine H2O, you have to make 2 bonds. So you'd have a p orbital and another p orbital. If you did that, the p orbitals are supposedly only supposed to go on the x-axis, the y-axis, and the z-axis. They only cross those 3 axes. And so with that in mind, if this simple overlap worked, H2O would have a 90-degree bond angle because the x-axis is obviously 90 degrees from the y or the z-axis. You would predict a 90-degree bond angle, but we actually see a 105-degree bond angle. So there's something going on. And for some of the more complicated atoms, say CH4, in order to make all the bonds we need for CH4, we would have to use 3 p orbitals, which you'd have x, y, and z, but then you'd also have to use the s orbital, which is just a ball in the center. And that would mean it would really screw up how this guy is connected. We really could not do that. And so what actually happens to get these obtuse bond angles, these is we form what's called a hybrid orbital. You know, when you hybridize a plant, you mix the gene of 2 different plants to get maybe a more resilient plant, a better plant, have better genome. Well, we're going to mix the properties of the s and the p orbitals together to get something a little bit better. Sometimes we're going to add in the d orbitals, but we're going to mix together two different types of orbitals and get an equal amount back of these hybrid orbitals. So example, if I mix two orbitals, an s and a p, I'm going to get two hybrid orbitals back. I took one s and one p, and I get two new orbitals back that are hybridized. If I take three orbitals and mix them together, I'm going to get three hybrid orbitals back. Now, while there is energy associated with making these hybrid orbitals will minimize electron repulsion. They will all be degenerate, which means they're equal in energy, and they will optimize the bond making. So the final structure is actually net lower in energy than what you would expect. So here's some example of these orbitals. These right here are what you call the hybrid orbital. You took the s and the p, and you get essentially this kind of like weird muscle man where they've worked out just the right arm. Didn't really do anything with the left. But these guys are allowed to make orbitals however they want, wherever they want, in order to make the maximum amount of bonds. So by mixing an s orbital and three p orbitals, we will get four new identical orbitals which we can use for bonding. Now, because it's an s and 3p, we're going to label these hybrid orbitals based on the mixing. So they form four sp3 hybrid orbitals. sp3, because it comes from 1s and 3p. 1s and three different p orbitals. This sp3 is going to be used in every tetrahedral shape. Every time we have the tetrahedral electron domain geometry, it's going to use sp3 orbitals. It doesn't matter if it's CH4, all bonds, NH3, three bonds in a lone pair, or H2O, two bonds and two lone pairs. All of these guys will be tetrahedral. Essentially, we took these. This guy is like carbon, has 4 electrons. 1, 2, 3, 4. We hybridize these guys together, and so we get 4 sp3, each with 1 electron in it. Each with 1 electron capable of making 1 bond. So right here we have methane. Here we have ammonia, NH3. Here we have our water. So we have 2 bonds and 2 lone pairs, each filling up a valence orbital. And this is why we have this tetrahedral shape, because we mix together 1s and 3p. sp3 had to do with 4 electron domains. Well, if I need to make 3 bonds, if I make 3 bonds, I'm going to use this 1s and 3p. I can do 1s and 2p orbitals, and I'll use sp2. And so our structure for sp2 is our trigonal planar. If I need to make 2 electron domains, so a linear molecule, I need 1s and 1p. So there's going to make 2 sps. So our basic structures are going to be related to the electron domains. What we'll get to, if I need to make 5 electron domains, I'm all out of p's. I got no more p's. I can't use any more p's. So what do I have to use? I have to use a d, because that's the next orbital available. So if I add one of the d's, I would get sp3d. And that's going to be our structure for the trigonal bipyramidal. And finally, 6 electron domains, I have to use a second D. And even if you don't understand this too well at this point, there is a little handy chart for the lab that shows essentially this little thing. If you know how many electron domains you have, you can figure out what hybridization it should be. If you know how many, if we know how many electron domains we have, we can figure out the hybridization, what it should be. So 2 electron domains, we're going to have sp. 3, we're going to have sp2. 4, sp3. 5, sp3d. And 6, sp3d2. More often than not, we'll only see the first 3 dealt with. More often than not. And what's further is these overlaps can be put in and described in 2 different ways. The main type of overlap is a singular lobal overlap. When 2 lobes of a bond overlap, just like that in the picture, this is called a sigma bond. Why do we need to name the most basic type of bond? It's because we can have some different bonds in there that we need to be able to deal with. But 2 S's overlapping, that's a sigma bond. An S and a P overlapping, that's sigma bond. 2 P's overlapping, like that, face to face over 1 overlap, that's a sigma bond. Any of our hybrid orbitals are all going to be sigma bonds. All of our hybrid orbitals. Basically, what it comes down to is the single bond is inherently always a sigma bond. A single bond is always inherently a sigma bond. And all atoms typically have mostly sigma bonds, where all the first bond between an atom is always a sigma bond. That's the first bond it'll make, the easiest to do. Now, why do we feel we need to introduce this sigma bond? Because when we have a trigonal planar state, which is our 3 hybrid orbitals, when we do this, we get the sp2 hybridized. You note that sp2 hybridized has a empty p orbital that is not hybridized. When we do this sp2, we take 2 out of the 3 p's and hybridize them up. The remaining p is still there. It is still there, and it's still, in this case, it is unused in the structure, in this trigonal planar shape. What we're going to see is sometimes that p does get used. That p orbital does get used. And so how are we going to do that? And that introduces the bond we will deal with. So if sigma bonds are single bonds, we're going to have a pi bond being our double and triple bonds. This pi bond is from an overlap of a double overlap, usually between 2 p orbitals. So if, as you see here, so this guy is sp2 hybridized. It's 2 trigonal planar molecules coming together. You have 2 p orbitals, one on one atom one on the other atom. Well, these p orbitals can then overlap over the top and overlap over the bottom. They fold in like palm trees to make a bridge over top of the single bond, over top of the sigma bond. So they are essentially nestling this up. The structure they are trying to draw and trying to picture here is C2H4. C2H4. Basically what we have a sigma bond, sigma bond, sigma bond, sigma bond. We have a sigma bond here, but we also have a pi bond. Essentially, we have between these two carbons, we have our single overlap. But these p, they're going to start to move in towards each other. They fold in from the top and the bottom, and we get this like bridge that's both over top and below our sigma bond, kind of nestling in it in the nook. Two hills surrounding our valley. And this is our pi bond, and this is our sigma bond here. And this is going to be true for every single molecule you draw. The single bond, the first bond between two atoms, is always a sigma. Any additional bonds you may see is a pi. So if we have a triple bond is made up of 1 sigma and 2 pi. A double bond is 1 sigma, 1 pi. And if there's just only single bonds, then it's only sigma bonds. Here's an example of a triple bond. For the linear diatomic molecule, you use an S and a P. It becomes sp hybridized. So it uses just one of the 3 P's. 2 P's still there. Each p orbital is 90 degrees from each other. So we still see the top-bottom overlap, but because we have another p orbital 90 degrees, we see a front-back overlap. So that sigma bond is nestled above and below, to the front and to the back of it. That sigma bond is really tightly held. This is why triple bonds take a lot of bond energy to break. This is why triple bonds are really strong and really short. Each time we add a bond, we are pulling the other molecule a little bit closer. A sigma bond, I'm like handshaking you. I'm getting your hand and we're here. If we want a socially distanced handshake, I can try to pull away as far as I can. Then if I'm double bonding, well, then I have to square up and I'm holding your other hand. This is as close as we can get. We can't get much farther away. I can't pull away without pulling you towards me. When we get a triple bond, we're just getting closer. So now I'm wrapping a leg around you, and now we're definitely a super spreader event. So as we're making more and more bonds, we're pulling the molecule closer and closer together, making it that much harder to break away. That higher of energy. But that's our simple, or as simple as we can, a sigma, pi, and pi bonds, and how they fit in with the valence bond theory. Now, here's why resonance structures exist. They exist because of the delocalization of the pi bonds within the p orbitals. So the structure right here is benzene, C6H6. You could draw this benzene like, let's see, since I've been kindly brought an eraser, you could draw a benzene carbon, 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 carbon. You can draw it double bond, double bond. So single bond, double bond, single bond, double bond, single bond, double bond, single bond. Or we could draw the structure double bond, single bond, double bond, single bond. So I've just shifted the double bonds around the ring to different atoms. Now this is allowed to do that because of the floppiness of these p bonds. They could fold one way and make the bonds you see on the left. They could flip and fold the other way and make the bonds on the right. And because it's easy enough to swap, we are going to result in the net effect of the whole thing just being one big whirl of electrons. We get a structure that is somewhat between the two because these bonds can change so easily. This structure is what? What is that? NO? It's NO3 or NO3 or CO. It doesn't really matter. The idea is that right here we have a lone pair and we have a double bond. We can move that lone pair into the double bond, kick the double bond out, and now we have a lone pair here. And if we do that, we see a resonance of all three. Some combination of all three such that we don't see any one of those three structures. This is only showing one of them, but we don't see just one of those three structures. We see all of them put together. What is the average of all three structures? What is the average of all three structures? So sigma bonds are stuck in place. Double bonds are delocalized. Now we can see some bond rotation in these hybrid bonds. Sigma bonds are capable of free rotation. This allows the adoption of various conformers, atoms with the same structure but different 3D shape. So if I'm just essentially holding on one hand, if I'm holding on not your hand itself but maybe onto your wrist, we can maybe twist and still have a reasonable grip. I can spin around just still holding your arm. But if I'm holding two hands, twisting becomes a lot harder to do. The same idea that, so this structure here is the same as this structure. We've just rotated it around this atom because it's all single bonds. But if I put a pi bond between there, if I rotate this at all, I can no longer overlap the pi bond. And so that's kind of locked in place. Before we do anything with this, the basic summary here. Every molecule will start with sigma bonds. Every single bond will be a sigma bond. If there is a double or triple bond, every bond past the first will be considered a pi bond. Every bond in addition to the first, in excess of the first bond, will be a pi bond. Sigma bonds are localized into one spot. Pi bonds are delocalized and capable of resonance structures. So that's a big thing. Now, this last subject, we'll go ahead and breach this very briefly. I'll look at the syllabus. We'll probably finish it on Friday. This is as hard of theory as it could be. That's as hard as the theory will get. I'm not sure I will even ask a test question. I will try to give you a hint if I plan on it. But this is the wave theory, really complicated stuff that if you were to progress far enough into what would be essentially physical chemistry, this is understanding why we have a lot of weird properties. And so this is the molecular orbital theory, which deals with how we treat bonding between multiple atoms. The hybrid orbital theory only treats each atom individually, but the molecular orbital theory looks at the molecule as a whole. The idea, when we put two atoms together, where essentially, remember, electrons are both a particle and they can act as a wave. And waves can undergo both what's called constructive interference, where the two waves add up, and destructive interference, where the waves cancel out. So whenever I mix two electrons together, they have some constructive interference, which is called a bonding orbital, and a destructive interference, which is called a non-bonding orbital. So we split into a high energy orbital and a low energy orbital, like this. So two S's at this energy, we split into a bonding, they overlap, or non-bonding, they don't overlap, like a positive and a negative. So we call that a sigma orbital, and sigma meaning a sigma bond, or sigma star meaning they don't overlap. It's the anti-Christ of orbitals. It's the anti-sigma orbital. Now, based on the number of interference orbitals in the molecular orbital diagram, we can calculate essentially what is the bond order and understand properties from this. When we fill these guys, it's just like our energy diagrams that we did back in chapter 4. We would fill them from the low energy to the high energy with all electrons that are in all the molecule. Depending on how they fill up, we can determine the bond order, which is simply half the number of bonding minus half the number of anti-bonding. And what this introduces that is new and not directly obvious, it is possible to have fractional bonds. Fractional bonds. So you have a bond that is somewhere between a single and a double, or a single and a half, a single and zero. Zero bonds would be like, say, 5 angstroms away. A single bond might be 3 angstroms away. Somewhere between the two would be, we have a bond that's actually 4 angstroms. It's not quite a single, not quite no bond. And we can see that, where the strength is proportional to what fraction of a bond it is. So if I have a bond order of 1.5, it would be stronger and shorter than a single bond, but it'll be weaker and longer than a double bond. And that's because we only have a partially filled orbital. But in practice, so you can use this it can be used to understand how stable a hypothetical molecule is. Right here, we have, I'm going to work these out. We have hydrogen, hydrogen plus, hydrogen minus, helium diatomic plus, helium diatomic, the 2 plus, and all of them have the same general setup. You need to count what is your valence electrons and put them in. Then you can figure out what is the bond order. So both of them have 1s. There's our sigma. There's our sigma star. Let's see, is that visible? Okay. So on hydrogen, hydrogen just has 2 electrons. So we're going to use those 2 electrons and fill this in from top to bottom. Hydrogen, there, that's our 2 electrons. Full stop, we are done. What does that mean? Bond order of hydrogen, 1/2 of 2. What's 1/2 of 2? That's 1. Bond order of 1. What do we know about hydrogen? We draw single bond, 1. What about hydrogen plus? Well, hydrogen plus means I got one of those electrons. If I have 1 less electron, what's that going to look like? We have hydrogen plus would have a bond order of 1/2. So essentially, it's like a little bit longer. If I made this hydrogen minus, I would have added an extra electron. So 3 electrons in. The bond order of hydrogen minus would still be 1/2, because you would have 1 minus a half. 1 minus a half. 1 minus the half there. So it's still 1. So it's still like the same kind of thing. Now, one step further. Helium. Helium has 2 valence electrons. So I put in 4 electrons. Bond order for helium. Bond order for helium diatomic would be 0. 1 minus 1 is 0. What does that tell us about helium diatomic? Helium diatomic does not exist. It does not exist because it would not make a bond. The bonding orbital and the anti-bonding orbital would cancel out and neutralize all bonding benefits. So it is not worth making a bond with a helium diatomic. And so helium is a gas that stays as it is. We'll finish up with these 2 and then be done. Helium plus, we would take away one of these. Helium plus, so it relates to plus would have a bond order of 1/2 again. So helium, if you could charge up a helium ion, it could make a bond with a neutral helium atom. You excite it, kick out an electron, you can make a diatomic. Is it stable? Ooh, that's question. If I made this 2 plus, I got rid of 2 electrons, then helium 2 plus would have a bond order of 1. So we're just taking what valence electrons we have available and putting them in this from low to high. The sigma cancels out, the sigma is canceled out by sigma star, and you could figure out what bonds are available. Would you ever, if ever asked about this on a test, would you ever have to draw a diagram? God, no. What might you have to do? You might have to put electrons in from top to bottom. You might have to determine bond order. But you would always be given a diagram if I even want to ask this. I might have so much other stuff that I don't need to. Well, either way, that's where we're going to stop for now. We will finish this up tomorrow on Friday. And that'll be that. And we can start chapter 8.